Good morning, everyone. Welcome back. So what we're going to do today is we're going to wrap up this last couple of examples from last lecture, and then we're going to get into the next topic, which is directional derivatives. So where we were last day is we were looking at the chain rule. So in other words, we're looking at derivatives where we've got compositions happening. So in this case, we're dealing with multivariable functions. So we could have that f is a function of x and y, but x and y are both functions of other variables. And so we want to differentiate the outermost function, the function f, with respect to one of the end variables it's a function of. And we transition through those intermediate variables, x's and y's. And that's what the chain rule tells us how to do. So for example, if we had that f was a function of x, y, and z, but x, y, and z are all functions of u and v, then ultimately this output variable, or this dependent variable w, is going to be a function of u and v, so we can look at its derivatives. And we get it by transitioning through the outer function and working out these corresponding derivatives in this way, piecing them together in this way. I just want to point out one thing. The example that we did last day, which was w is f of u, v, x, and y. And then we wanted to work out what is the derivative of w with respect to x. So we did that by taking the derivative of that function with respect to u, and then u with respect to x, and then the derivative of the function with respect to the next variable, v, and then v with respect to x, and so on. I had w's up top. It's, as we discussed after class, there was a few students who were talking about this. It's best if we use an f there for that derivative on the right-hand side, because essentially what we are doing is we're saying, I want to find the derivative of that variable w with respect to x. And so I'm going to do that by dealing with the outer function f, differentiating that outer function with respect to one of its variables, u, and then the derivative of that variable, u, with respect to x, and then so on down the line. And so that's why I've replaced these w's with f's up top. The reason this sort of came up is because the last line, if we left w's on the right-hand side, it looks like we get this expression, the derivative of w with respect to x is a bunch of stuff plus the derivative of w with respect to x. And that kind of doesn't really make sense if those derivatives canceled off, and they don't. It's the derivative on the left is w with respect to the ending variable x, whereas the derivative on the right was really meaning that derivative of the expression f that was, combining the u's and v's as x and y's together. So I just wanted to make that slight change there, changing those w's to f's. Okay, so then we ended off with last day the idea of an implicit partial differentiation. Here, what I want you to just think of surfaces like x squared plus y squared plus z squared equals 1, so a sphere, or this kind of surface, x squared plus y squared minus z squared equals 1, or the other quadric surfaces we looked at, where we don't have z explicitly written as a function of x and y. We've got the z, the x's, and the y's, and they're all mixed up together in the same equation. So that's an implicit function. We're thinking of z as being implicitly defined in terms of x and y, rather than explicitly, where we can immediately see that whatever the x, y values are, they give this as the z value. Here, whatever the x, y values are, the z value is implicitly determined by the equation that's relating them. And there could be more than one z value that comes out. So we're thinking of this as z as implicitly defined by x and y. And then we have to specify which z value we want if there's more than one. So we can still do differential calculus on these things, much like we did in Calculus 1, the idea of implicit differentiation. It's just that we're now going to see how we can actually get these derivatives out using the chain rule.
Jamie,
Yep.
I have a question about why we use capital F.
Why do we use capital F here? That's a good question. So we can use lowercase. Either one is fine. The way I typically use this notation, and I think James Stewart does the same in the textbook, is when we're using capital letters, we're ultimately thinking of these things as level surfaces. So for example, I've got this surface here, which I'll just highlight. I've got this surface here, and I'm in some sense thinking, that's a sort of a meta level here. I'm saying think of this thing and now think of what's going to come from it. So we're ultimately thinking that z is a function of x and y. Now there may be more than one function here. So for example, if this was a sphere, x squared plus y squared plus z squared equals 1, there's sort of this upper hemisphere and this lower hemisphere. And so I'd really get two functions. Z is 1 minus the square root of 1 minus x squared plus y squared, or the bottom hemisphere is, maybe I'll just put the plus there and then write these things out. So if I make that a plus, we can think of z as a function of x and y. In fact, there's two of them. There's z is equal to the square root of 1 minus x squared minus y squared. And there's another function, z is equal to negative square root of 1 minus x squared minus y squared. And much like in Calculus 1, we don't want to always take these surfaces and have to split off the various functions and then say, okay, now I got a point on it. Which function am I going to use? Because if it's on the lower hemisphere, I use the second function. If it's on the upper hemisphere, I use the first function. We don't want to have to do that. We just want to deal with the expression by itself. So where does your question come into this? Your question comes in right here. Whereas if I'm thinking of z as a function of x and y, I could think of it as like, this is little f of x, y. Or I could think of this as like little g of x, y. And so those are where I would use these lowercase function values to just say, okay, I'm thinking of z as a function of x and y. Here's the various functions that we can have. But I'd rather just work with the original equation. So if I work with the original equation, then what I do is I say, well, why don't I just take this thing as my function, and this surface is therefore the value of this function, or all values x, y, z for which this function is 1. So it's a level surface. So if I call this capital F, X, Y, Z, then I can think of the surface as, or the sphere in this case, as the level surface f, x, y, z equals 1. And so this is sort of the general form of these kinds of surfaces, these surfaces that we get from these implicit descriptions. Is there something of the form a function of x, y, and z equals 1? So I'm thinking of them level surfaces. And when we do this, it's typical, or it's classical, to use capital letters for the functions, because there's another function level going on here, in that the third variable z is really a function of x and y, and we get that by dealing with this outer wrapper, this sort of big capital F function, and then we can tease off little individual functions for the various patches of the surface. But at the heart of it, we're kind of thinking of this as, now it's a level surface. It's this function of 3 variables and 1 output, so this object in 4 dimensions where we're cutting out all the values of x, y, and z for which that function is 1. So we're cutting out a 4-dimensional space, some 3-dimensional object, which is the level surface. Does that answer your question?
Yes, thank you.
Long-winded answer, but but yeah. So it's you could use little f. We use capital F just to signify the fact that there's this sort of level structure going on here. There's some bigger object we're considering, and we're trimming out of that the thing that we're interested in.
Okay, thank you.
You're welcome. Okay, so then with this kind of object, this, what we're going to call a level surface here, we're thinking of our surfaces now as a level surface of a larger object, we can still get its derivatives. And the way we do that is, as we've calculated here, we start with the equation that defines our surface, and then we just differentiate through. And when we differentiate through, we use the chain rule. So the derivative of the left-hand side is the derivative of the outer function, capital F. Its derivative with respect to x times the derivative of the x variable with respect to x, and so on along the line. And when we do that, we get the derivative we are really interested in finding. How does z change with respect to x, for example? And we can solve this equation, and we get that the derivative of z with respect to x is obtained by taking the derivative of that outermost function, that capital F function with respect to x, and dividing it by the derivative with respect to z, and then slapping a negative sign on front because of the algebra that was involved there. And we get the same thing for the derivative of the z variable with respect to y. So let's see an example of these kinds of things. So let z be the function of x and y such that it satisfies this equation. So this is our surface that we're interested in. And what we're then going to do is say, let's just call this part of it f of x, y, z. So then what we're interested in is this surface. It's a level surface. It's all of the, well, it's the zero values of f of x, y, z. It's all the values of x, y, and z, which you plug into this function, they return 0. So if I plug x equals 2, y equals 4 in, what I end up getting is, so at x equals 2, y equals 4, we plug it in and we get z cubed minus z plus 2 times 2 times 4 minus 4 squared, and that's got to be equal to 0. So we're going to see what are the corresponding z values. We get z cubed has to, minus z is equal to 0, or in other words, z cubed is equal to z. Or in other words, z could be 0, 1, or minus 1. Those are all solutions to that equation. And so since those are all solutions, which one are we interested in? Well, that's where this extra bit of information is telling us we want to know the point corresponding to, well, the z value that is the one corresponding to the values of x equals 2 and x equals 4. So I'm just going to bring across, this is what the object looks like. This is the set of all x, y, z values that satisfy that equation. And you can see it folds in on itself. So it folds in on itself. So it's not the graph of a function, because for a given x and a y value, there can be multiple z values. I just look at a vertical line. It passes through this surface multiple times. So there's multiple z values. And in fact, when x is 2 and y is 4, we get what seems to be 3 z values. There's one right here. There's the yellow one that I've identified. That's the one with a z value of 1. Then there's the one with z value 0. And then there's one down below here with a z value of -1. So we get 3 of those. So we just have to identify which point we're interested in. So there's the point we're interested in. And we'd like to find things like the derivatives, tangent planes, linear approximations, all that kind of stuff for this. Okay, so then what do? Well, if we want to find the linear approximation, we need to find the derivative of z with respect to x. We also need to find the derivative of z with respect to y. How does z change with respect to x? How does z change with respect to y? We put those into our tangent plane formula or linear approximation formula, and we get all of our results that we want. So we just need to know this value. The problem is the z is not explicitly written in terms of x and y, so we can't just go and straightforward differentiate some function of x and y. They're all tied up together. So that's where we use that previous result that says it is the x derivative of that function capital F divided by, sorry, I wrote y, I meant to write z, divided by the z derivative. So scroll back up. That's what that's telling us. To differentiate, find the derivative of z with respect to x, it's f sub x over f sub z with the negative sign there. Now, if you forgot this formula, which can happen, I mean, I actually don't memorize this formula. I just think about how I derive it each time. That's not entirely true. When I give the lecture and then the subsequent weeks in the semester around this, I just remember these formulas. But then, a couple of years pass and I want to do this. I don't remember the formula. All I do is the following. I just take this. So this is always just a good handy thing to remember. I take this thing and I think to myself, well, I want to find its derivative with respect to x. So we go ahead and differentiate both sides. I'll move this over a little bit. Derivative with respect to x of the 0. And so that becomes a 0. What's the derivative of this side with respect to x? We just go through and we can do the derivative. So it would be the derivative, I'm thinking of z as a function of x, so it's 3 times z squared times dz dx minus dz dx plus the derivative of this expression with respect to x is 2y, and then you do a product rule, but the derivative of y with respect to x is 0, and then the derivative of the next piece, that's also 0. And so then you could solve. You could get del z del x is equal to, and you sort of move things around. There's a negative 2y that comes over, and then we get a 3z squared minus 1. Okay, and so that's how we could do it. And then if we think, well, where did these things come from? What's up top here? I'm just going to ignore the negative for a second because that just came from when I moved it over. That thing sitting up top, that 2y, what is that? That is just f sub x. That was the original whole expression, z's cubed minus z, blah, blah, blah. That was that whole thing where I just differentiated with respect to x. And what's sitting down here, well, that was just the whole expression when I differentiated it by z. So that's where these things are coming from. So there's not a mystery here, in other words. This formula just didn't come out of the blue. This formula is just coming from differentiate both sides with respect to the variable and do your chain rules as you go along. So if you forget this formula and you're like, I'm stuck, I don't know what to do, you do know what to do. You just go ahead and you differentiate through. The formula just gives us a nice, quick, handy way of doing this. And it's good to remember in the short term because it's quick. We just know exactly what we need to do. I write it down, negative fx over f sub z. So then I look at my expression and say, what's the derivative with respect to x? That's 2y. What's the derivative with respect to z? 3z squared minus 1. And there we go, we're done. If we forgot the formula, we just do it the long way. Get the same answer. Similarly here, this is negative fy over fz. And that's going to be the derivative of the expression with respect to y. So that's negative 2x, and then I'll put the brackets around here, minus 2y. So that's our capital F function, derivative with respect to y, all over the same thing, the derivative with respect to x. Now, what we are interested in, I'm just going to move this over because I want a little bit of space beside it. We are interested in the case of the derivatives at 2, 4. What are these derivatives at the particular values x equals 2, y equals 4, and z equals 1? So now we can pop these things in. When y is 4, this is negative 8 over 3 times 1 squared minus 1, or in other words 2, or in other words negative 4. Let me see. Yep, got that. Okay. Sorry, I was just making sure I got all my signs right. For some reason, I thought I dropped a sign there. Okay, so we got our result, and we do the same thing for the next one. So del z del y at 2, 4. We pop these values in, x equals 2, y equals 4, so that becomes a 2 times 2 is 4, minus 2 times 4, so minus 8. So 4 minus 8 is negative 4. With the extra negative up top, gives us a 4 up top. We have our 2 at the bottom, so we get our value of 2. So we have both our partials. Now we can go for our linear approximation. Our linear approximation is, we called it L of xy. That's obtained by taking the z value of the point we're approximating at, plus the derivative with respect to x times x minus the x value of the point we're at, plus the derivative with respect to y times y minus the y value of the point we're looking at. And so there is our linear approximation, which we can simplify it a little bit. I get the -4 times the -2 is 8, and that cancels with the -8 from the next term. So we get this expression here. And so there's our linear approximation. So nothing new in this next step. This linear approximation, that's all stuff we've done before. We just need, the only new stuff here was how to get the derivatives in this implicitly defined function form. So as a level surface, rather than z explicitly defined in terms of x and y, they're now all tied up together. So that's the new part, just how to extract the derivatives. And once we've got the derivatives, we can get our approximations in the same way. So we're going to use our answer now to find the approximate value for z. So z is approximately given by the corresponding linear approximation values, 3.96. Okay, so this is the value we want to find. What is our corresponding z value at these xy values? That's given roughly by the z value on the linear approximation. So then I get 1 minus 4 times. And this is where I much prefer to use the line before. So I'm going to use this line before here. And the reason I much prefer to use that is because it's got the difference in there. And that's really what we care about, is these differences. So this is 2.02 minus 2. So that's 0.02 plus 2 times 3.96 minus 4. So that's negative 0.04. Or in other words, 1 minus 0.08 plus, actually that's a minus now, minus 0.08, or in other words, 0.84. So that is our rough value there. Now, when you're doing these kinds of questions, I really do want you to think, what's going on? What's happening? What are these numbers telling me? And so part of this is, we can just think, I'm standing at the point 2, 4. X equals 2, y equals 4, and a particular z value. I'm not too concerned about the z value just yet, because I want to sort of know how things are changing. What do these numbers -4 and 2 tell me? -4 tells me that if I'm standing at that point 2, 4, and I move 1 unit in the x direction, then I'm going to drop -4 units down, right? That's the slope in the x direction. So moving in the x direction causes me to descend by -4. The other part is the derivative with respect to y is if I move in the y direction, I ascend 2 units. So for every unit increment in the y direction, I jump up 2 units. So these two are telling me that there's sort of a battle going on here. If I move in the x direction, I drop. If I move in the y direction, I increase. So what happens if I move to this point? Well, I move 0.02 units in the x direction. And for each of those units, I drop by 4. So I'm actually going to drop by 4 times this number, so negative 0.08. So I'm going to drop by negative 0.08. But then the next one, if I move from 4 to 3.96, I'm moving in the negative y direction, 0.04. And for every movement, this 2 tells me that if I move in the positive y direction, I jump up. So it's telling me that if I move in the negative y direction, I'm going to drop down, right? This is slope. This is telling me the slope is 2. So if I move in the positive direction, I go up. Or conversely, if I move in the negative direction, I drop. So here I'm moving backwards 0.04. And for each unit I move backwards, I'm going to drop by 2 units. So I will have dropped in total by negative 0.08. And so in both cases, I'm dropping by 0.08, and for a total of negative 0.16. And that's what we see down at the very bottom of the page. But I can see this already, what's happening. And that's what linear approximation is telling us. How does our z value change when I move in various directions? And that's what derivatives are. So this is all just slopes. This is all just slopes and movements in directions and seeing how things increase or decrease. That's the geometry behind this. So when you're doing these calculations, don't go through them blindly. Think, what does this mean geometrically? What is this telling me? when you're guided by that, you can't make a mistake, right? You know exactly what's going on. You know why you're doing the calculations you're doing. You know exactly what they're informing you of. So just keep that in mind as you're doing these things, to think about what's going on and what the geometry is. Let's look at the, yep, go for it.
I had a question. So for dz, dx,
Yep.
2 and 4 is x and y, right?
2 and 4 is x and y, yeah.
Okay, and the z value is 0, 1, or -1?
It's right here. So you see in the question, we were given the z value. So we're always using that one.
Oh, okay.
Yeah, and so that was, it's a good point. So thanks for bringing that up again. That was, the idea is that we're interested in this point. If I was to change my z value, so if I change it to 0, then that puts a different point on this surface. Or if I go to -1, that's a different point. But in this question, everything we're interested in is at this point here. So we're always going to use the z value of 1. And thanks for allowing me the opportunity. I forgot I was going to do this. So we worked out the equation of the tangent plane, so we can plot it, and we see that that's exactly what we get. So all the information we're using is about this point, and that gives us that tangent plane. If I change the z value to a different one, I get a different point on the curve. This tangent plane is now no longer the tangent plane for this point on the curve. We have to recompute what the tangent plane is for that different z value. So all of this is happening for the z value of 1. Yeah, thanks for bringing that up. Good point. All right, let's have a look at the next one.
There's another question in chat, if you could
Oh,
answer that.
sure. So is it okay to implicitly differentiate as the derivative with respect to x times dx, derivative with respect to y times dy, derivative with respect to z times dz? And then once you've got that, then you have to realize that you are differentiating with respect to a particular variable, say x in this case. And so if you ultimately, so what you've written down here is what's known as a differential form. And then we still have to identify what the variable is we're going to differentiate with respect to in the end. So if we're going to differentiate with respect to x in the end, there would be under each of those final dx, dy, dz at the end of each of those terms, there'd be a x underneath it. So it'd be a dx, dx, dy, dx, dz, dx. And then that gives us the same expression we have. So yeah, that's fine to write it that way, but then you have one extra step now you've got to do the final derivative with respect to a particular variable. All right, let's have a look at this next one. So this next problem is, I mean, you look at it and you might think, whoa, what's going on here? I've got, okay, the equations x equals something in u and v, y equals something in u and v. They're telling us that those explicitly tell me that x is a function of u and v and y is a function of u and v. But the next line says that these also define u and v implicitly in terms of x and y. So what that means is if I give you an x and a y value, then we get these two equations which we then solve for u and v. So u and v are also functions of x and y, but they're implicitly defined. You got to go do some work to get the actual u and v values for a given x and y. And so these are relationships. They tell us how to go from uv values to xy values, but they also tell us how to go from xy values to uv values. And in particular, we're interested in the case around xy equals 2, 0 and uv equals 1, 1. So what is this really, what's really going on here? This is actually what we call a change of variables, or in other words, a change of coordinates. This is telling us that if we're in one two-dimensional system, x, y, then I can take those points and remap them in another coordinate system of u and v, and vice versa. I can go from uv coordinates to xy coordinates. So these are what are known as a change of coordinates. Or we could think of this as a non-linear transformation. In linear algebra, you will have studied linear transformations, how to take, uv values and produce xy values in a linear way. So x is some linear combination of u's and v's. Y is some linear combination of u's and v's. These are not linear, so we call this a nonlinear transformation. So what we're actually doing here is we're developing the tools needed to study nonlinear transformations. In other words, to generalize the ideas from 232 in the case where things aren't linear. The way we do that, I'm just giving you a highbrow sort of overview. The way you do that is at a particular point, let's say 2, 0, 1, 1, in this case, x, y, and the UV values, is you use derivatives to linearize things. And when you linearize things, in other words, make linearizations or tangent plane approximations, then you've made things into linear objects, and now you can use linear algebra to study those things. So the big picture perspective of how this course fits in with linear algebra is curvy objects we first make flat using derivatives, and then we use the tools from linear algebra to study the flat objects, the linear objects. So we're not doing the whole ball of wax here, but I'm just sort of setting the stage that this is sort of the big picture perspective on why we're sort of considering this kind of complicated structure of functions and many variables sort of floating around. I agree, when you look at this, it looks quite complicated, but we just want to be able to build the tools up that allow us to analyze these things. So here's the big picture perspective. I've got now that u and v are implicitly defined in terms of x and y. So given some x, y values, I could construct their corresponding uv values when our x, y values are close to 2, 0. And now I want to know that if I change my y value a little bit, how is my u value going to change? So what is du dy at that point 2, 0? If I change y a little bit, how does the output variable u change? And then the next one says, now I got a function of u and v. If I think of u and v as functions of x and y, then z is ultimately a function of x and y, and so I can work for getting its derivative as well. So that's sort of the big picture perspective here. We're looking at change of variables and then how variables change relative to the change of the input variables. So how do we do this? Well, this is the object we want to find, du dy. So now I have to think, how can I get that? Well, I just really want to take derivatives with respect to y. So there's only two equations that I have. I have an x equals uv plus v squared equation. I'm going to make a little bit of room in front of it by moving that over. And I have another equation, y is equal to u squared minus uv. So those are really the only two things I have. And I'm interested in y derivatives. So let's go ahead and compute the y derivatives of these things. After all, they're the only two things I know. So they're the only two things I can work with, which means they're the only two things I can differentiate. So let's see what happens when we do that. So those are the two expressions we're going to differentiate. The first one, the derivative of x with respect to y. Well, x and y are independent variables of each other. They point in two different independent directions. They're orthogonal to each other. They represent different variables. They're not related to each other in any way. So when I take the derivative of x with respect to y, it's 0, as usual, since we've been doing partial derivatives. How about the next piece? The derivative of that expression with respect to y. Well, I'm differentiating through this expression uv plus v squared with respect to y. So I'm going to have to do a chain rule here. I'm interested in this case in doing our full derivative. So what I'll do is I'll say derivative with respect to y. So that's going to be, the first one is a uv, that's a product. So it's going to be the derivative of u with respect to y. And then, sorry, that should be a y, not a v. The derivative of u with respect to y times v. And then plus u times the derivative of v with respect to y. And then I've got a plus. The derivative of v squared with respect to y is a derivative of the outside, which is 2v, times the derivative of v with respect to y. So that's our first equation differentiated. Okay, we just went through and we're differentiating everything with respect to y. Now we can see the thing we're interested in is du dy. That's here. And oh, the other ones are v with respect to y. So that's the one we want. We're trying to find that one. And this will allow us to write it. So maybe I'll just put it over here and make some room. This will allow us to write du dy in terms of the other ones. But what I'm going to do is I'm going to solve for dv dy. So I'm going to solve for dv dy. How do I get that? Well, I move the other expression to the other side. That gives me a negative v. Then I divide by the coefficient of the dv dy. And I get this expression here. So all I'm doing is taking that previous equation and isolating one of the derivatives in terms of the other one. And I chose to isolate dv dy in terms of the other one. Okay, we can do the same thing for this next one. dy is 1. This is going to be 2u du dy minus the derivative of the first, du dy, times the second minus the first times the derivative of the second. And again, I get an equation relating the two derivatives. So I can solve for dv dy in this case, like I did for the other one. And in this case, my solution for dv dy, let's identify where it is. Here it is. So what do I have? If I move the other things to the other side, I get 1, and I get a minus 2u plus, maybe so I just want to make sure, I want to group it all together. And so I got a 1, and then I'm moving the 2u du dy minus the du dy v to the other side. So I get a negative 2u and a plus v, and that's times the du dy. And what else do I have? So that's moved everything over except for the dv dy, and that has a negative u in front of it. So I've got to divide through by that negative u, which is this thing here. So I'm just doing a little bit of algebra here. So I end up getting this whole thing divided by negative u. So some expression like that. And that's another expression for dv dy. And so now I've got these two expressions, and they're equal to each other because they both equal dv dy. So these are equal. In particular, they're equal at the point uv equals 1, 1. So they're equal, and I'll say comma, at the point uv 1, 1. We get the following. We get that the 1 plus negative 2u plus v, so that's negative 2 plus 1, so that's negative 1 times du dy all over negative u. U is 1, so that's all over negative 1. So that means I can slap some negative signs in front here, is equal to the other expression, negative v, which is negative 1, all over u plus 2v, so that's a third, and that's du dy. So I've set those equal to each other and plugged in u and v, and now that gives me my single equation in du dy. And so that's what I can go ahead and now solve for. So what do I have? I have, bringing all the du dy's to one side, I get a 1 plus 1/3, and then on the other side I get a 1. So that tells me that du dy is equal to, what do we get? 4/3, bring 3/4. So 4/3 on the side, and then moving it over, we get a value of 3/4. Okay, so that was a lot of work to get a derivative, but the idea was that these variables u and v were tied up together with the x's and y's. If I need to know how u changes relative to y, well, I need to use both equations because they are linking u's and v's and x's, y's all together. It's a change of coordinates, so they're all dependent on one another. So I have to use both equations and then bring the results together. So once we've got that, we could do the following. We could say, this wasn't asked for, but we're actually going to need it. Once we know du, dy, also we can get dv, dy. That's equal to -1/3 times du, dy. And du, dy is 3/4, so this would be -1/4 for dv, dy. So I get both. I can get both. How u changes with respect to y and how v changes with respect to y. Why do I need both? Because the next example or the next question is asking us, what is the derivative of z with respect to y? So the derivative of z with respect to y is equal to z is u squared plus v cubed. So this is saying z is a function of the variables u and v, so in that coordinate system. But we want to see how this function z behaves in the other coordinate system. So when I replace u and v with their functions of x's and y's, how does z change with respect to those variables? So del z, or dz dy, is dz du, du dy, plus dz dv, dv dy. And this is dz du is 2uv cubed. Du dy, I'll just keep that as du dy for now so we don't do too many steps all at once. Dz dv is 3u squared v squared times dv dy. And now we plug in u, v equals 1, 1. Du dy equals 3/4, and dv dy is equal to -1/4. And we plug all of those things in, and we get dz dy is equal to 2 times 3/4 plus 3 times -1/4. In other words, let's say 6/4 minus 3/4, or 3/4. And so that's how z changes with respect to y. If y increases by 1 unit, then z increases by 3/4 of a unit. Okay, so this took, and I completely missed, this takes our chain rule and the stuff we developed this course and takes it to the max. This takes it to the extreme. And these are the kinds of questions one encounters when one needs to do a change of coordinate system and try to figure out how a function is changing relative to one set of coordinates and how that means it's changing relative to another set of coordinates. So this is an extension of linear transformations, all the things you study in linear algebra, but this takes it to the next level and does it for nonlinear transformations. Yeah, this is some heavy stuff. I completely agree. That's why it was saved to the last example, but it's where this material starts to converge with linear algebra. And this is where this kind of stuff gets used moving forward. The question in the chat is asking about this line here. Where did I get this line? What I did was I just used algebra on this previous line. And I said I'm going to take the du dy and move it all to the left-hand side. So there's currently a +1 du dy. And then when I move the -1/3 over to the other side, that adds another third du dy. And then I took this -1 and moved it to the other side, becomes the 1. So it's just algebra at that step. I know sometimes it's hard to decipher what's being algebra and what was calculus, but that was an algebra step. Okay, so this next topic, I didn't anticipate spending this long on this one, but the next topic is directional derivatives. So the idea with this one is the following. it's taking our results.
Excuse me.
Yep.
Hi. There was one more question about the last example. This is Niloufar, by the way.
Yep, I know. The previous line,
Like the one circled in purple.
the one in purple. Oh, that came from setting these two equal. So this, I'll highlight those in purple. So this thing, because it's dv dy, that's equal to this thing. So those two expressions are equal to each other. And so what I did was I just took this expression and wrote it over here, but at the same time plugging u and v equals 1, because that's where we're interested in. We're interested in when u and v is 1. And then this expression, I just rewrote it down here, again, plugging u equals 1 and v equals 1 into it. Because those two expressions have to be equal to each other. They're both equal to dv dy. So those expressions have to be equal to each other, and moreover, they're equal to each other when u and v is 1. So rather than writing the whole thing out again and then plugging in 1, we can just plug in 1 and then set them equal to each other. All right, let's have a look at the directional derivatives. So what are directional derivatives? Well, I'm going to do it with a picture like we did before. So I've got this surface in blue, and we're used to seeing a picture like this, where I just take a plane that's in the x direction, so at some particular y value, and I slice the surface and it gives me this black curve. And that black curve, we can work out its slope of the tangent line at the given point. That's its partial derivative with respect to x. We can also look at the curve that's in the y direction, and the slope of that curve at the given point there in red is given by its partial derivative with respect to y. But there's nothing preventing us now from taking this idea and just doing it in general. What if I take any slice through that point in any direction whatsoever? That still results in a curve. So maybe I'll bring one out sort of there, and we'll look at it from a side view. That still results in a curve, that black curve. That curve still has a slope of a tangent line at it. And so that's what we would call the directional derivative, the rate of change of the z value in that direction, where the inputs x and y move in that direction. So that's what a directional derivative is. It's just the derivative in an arbitrary direction, not the x direction, not the y direction, but any arbitrary direction. So a picture of this could be something like, we've got our point, we've got our x direction, we got our y direction. So I'll go down here. There's our I hat, there's our j hat. And I'm interested in, what if I move in an arbitrary direction, say u? What's going on in that direction? How is the slope of the curve in that direction behaving? That's what a directional derivative is. How the z value is changing as I move off in that particular direction. Okay. This is closely related, as we will see, with the idea of a topographical map and trying to infer from the topographical map some information about steepness and maximum steepness. So imagine you're on Burnaby Mountain climbing up one of the sides of the hills, and you're at this point P. Which direction is the steepest ascent? So these topographical maps are drawn in such a way that these curves are level curves. They are curves that represent the trails that are all the same elevation. So if I move off in this direction or in this direction, I am neither gaining nor losing altitude. I am maintaining a constant height above sea level, if you will. So what would be the direction of steepest descent? Well, I look at, see where the next level curve is, and I move in sort of this direction that's perpendicular to the one I'm on, and I move into the direction of the next highest level curve. And then I keep going. Each time I'm going to move perpendicular to the level curve I'm currently standing on. So there's a whole bunch of right angles here. And so that's the curve of steepest ascent. Why is this connected to directional derivatives? Because in some sense, this is about, there's a surface, a mountain structure here. I'm at a particular point, and I want to know which direction do I have to walk in to get the steepest ascent, to get the steepest slope. So this is about moving in a direction with maximum directional derivative. And so that's the tie-in here with directional derivatives. And we'll see that this is related to the partial derivatives in a rather nice way. So I'll get to the definition of directional derivative, and we should be able to do in the remaining minute and a half or so an example of this. So what is a directional derivative in terms of the definition? Right now I sort of gave you an informal idea, but what is the actual rigorous definition? So first I'm writing down the definitions of the x and y partials. That was take our function, move a little bit in the x direction, so x naught plus a little bit, and take the difference quotient and see how the limiting behavior of that is. And that's the x derivative. Do the same thing when you move a little bit in the y direction. Take the limit of this difference quotient, that's the y derivative. But a directional derivative says you want to be able to move in an arbitrary direction. So what we do is we move in the direction of a unit vector AB. So that means we move a little bit in each of the xy directions. So a times h in the x direction, b times h in the y direction. And I'm interested in the value of this limit. That's our directional derivative. So how do we compute this? How can we compute this? Well, the idea is to convert it back to a problem we know how to do. I'm going to let g of h be x naught plus ha, y naught plus hb. In other words, I'm letting g of h be this expression here, this whole thing. Why is that? Because we're working out a limit with respect to h. So I'm just thinking of that whole difference quotient as a function of one variable. The one variable is h. So this is just a one variable calculus problem from calculus 1. So if I let g be this, then the first observation is that the directional derivative, that definition written up there, is the limit as h goes to 0 of g of h minus g of 0 all over h. I just pop in what those things are in terms of g rather than f, and we get this, and that's just g prime of 0. So that's the first observation, is that the directional derivative is just this one d calculus derivative. The second observation is to say, well, if I'm interested in g prime of 0, then let's compute it. What is the derivative of g prime of h, first of all? That's d dh of this expression. And now this is just a chain rule problem because I want to differentiate this function with respect to h. That means it's the derivative of the function with respect to x times the derivative of the x function with respect to h. But the x function is x naught plus ha, which is linear, so its derivative is a. And similarly for the other part. That's the derivative with respect to y times b. Or in other words, we get that, actually I'll do one more line here. When I plug in 0 now, this becomes del f del x at x naught y naught times a plus del f del y x naught y naught times b. And so that's our directional derivative. We more succinctly write this typically in this way because it looks like a dot product. We might as well just write it as a dot product. The only thing is I just have to make up this new name for the vector of partial derivatives. And when I do that, we can now recognize it as a dot product. So this upside down triangle with the arrow on top is called the gradient. And so this notation is just the vector of partial derivatives. And so that is how we can compute a directional derivative. We take the two partial derivatives, the partial with respect to x, the partial with respect to y, which we know how to compute already. And then we just dot it with the vector in the direction we want to find the derivative of. So it's just a nice dot product of the gradient vector, the vector of partials, with the direction vector. So I'll leave it there, and then we'll do some examples next day related with this.